Hey everyone, I apologize for the homework because we're running into some problems that we're gonna have to figure out. Uh, but basically, I wanted to spend a few minutes talking about why we're having this problem, and it comes down to all about how humans and computers each store numbers. If you think about it, this way, if you think about this, humans store numbers by writing them down, remembering, or even putting them on a web page. Oh my goodness, there's so many digits for pi. Hey, and as long as we've got space where we can write these digits down, we can keep track of them. All right. So we're limited by our limits are the size of our paper, if you will. But for computers, when computers are writing numbers down, they actually think about data in terms of bits and bytes. So that means it's a string of zeros and ones. Okay, now that means that the limit on the size of a number that it comes to is determined by how many bits do I care about. And it turns out for most computer programs, the number of bits that it cares about means that somewhere around 10 to the minus 14, computers say, yeah, that's pretty much 0. And anytime you try to calculate something smaller than that, you either get, hey, that's just 0, or you get not a number. Okay, so let's just we're going to look at our problem here and see how we're running into that problem. So we've got an interatomic spring spacing, we've got interatomic spring constant, I should say, we've got our interatomic spacing between atoms, and we've got our time step. And both of these numbers are approximately what you should have gotten in class. And this number is what we say, hey, that's a good time step for atomic things. So what is the impulse for the first delta t? And I'll also ask, what's the force? And so the force is just going to be the interatomic spring spacing times the atomic spacing times 0.2, because we said we are going to displace it 20% of the way over. So if we go ahead and plug numbers into this and calculate, we get something like 2 times 10 to the minus 10 newtons. And while this is a small force, our computer says, okay, I can deal with that. But the moment we multiply it by our small time step, we get 2 times 10 to the minus 24 Newton seconds, and the computer says, oh crap. So we got to figure out what the problem. And really the problem is that SI units are decidedly inconvenient for this problem. SI units are also often called MKS units because all units in mechanics are based on three things: a length, a mass, and a time. and it's called MKS units because the length is always meters, the mass is always kilograms, and the time is always seconds. So, when we look at these, that's where the MKS comes from. Cool. So, we're not going to be able to use these because meters, kilograms, and seconds are not meaningful on an atomic scale. We should use, for lack of a better term, what I'll call atomic units. There is actually a term called atomic units in physics, but in order to really talk about them, you need to know about charge first. And while you all know about charge, I'm not going to talk about charge units. So just know that if we talk about atomic units in Physics 2360, we're going to say, oh, by the way, these are real atomic units then. So as we are thinking about this, we're going to remember our tiny prefixes. The prefixes that we're going to remember are nano, or 10 to the minus 9, pico, or 10 to the minus 12, femto, or 10 to the minus 15, and atto. Attaboy. Or 10 to the minus 18. That was a terrible joke. Okay, and so we're going to remember these prefixes while we build new units. It turns out that maybe for our length unit, since we're talking about atomic lengths here, we should use nanometers. And maybe the time units, let's use picoseconds. And for our mass, let's use attograms. So we'll call our new units the NPA unit system, which doesn't have a cool sounding acronym that I can think of, but maybe you're more creative than me. So we've got these different quantities that we have in our problems: the interatomic spacing, the time step, and the mass. And so we're gonna look at the new unit in the NPA system. So instead of D being 10 to the minus 10 meters, it will be 0.1 nanometers. Instead of dt being 10 to the minus 14 seconds, it can be 0.01 picoseconds. Instead of masses being 10 to the minus 25 kilograms, they can be 10 to the minus 4 attograms. And you can see the numbers that we are getting here are much more reasonable. It's hard to imagine multiplying these things together and getting close to that 10 to the minus 14 oh crap line that a computer is going to start choking on things. So what I want you to do is think about what would a unit of force be, and what should our unit of momentum be? And put these units in terms of these NPA values. And that's actually going to become part of your homework. What is the new force unit for this new system of units we need to use? What is the new momentum unit for this new unit system we're going to need to use? The program is actually not going to change a ton. but it will be able to then, but when we change to a new unit system, we'll be able to solve this physics problem better. All right. Thank you very much. Have a great day.